Welcome to this week's Journal Club. The paper we'll be discussing in today's Journal Club is titled Addressing Loss of Plasticity and Catastrophic Programming in Continual Learning. This paper was published at ICLR 2024. In AI, catastrophic programming is a key challenge where models forget old knowledge while learning new tasks. My research focused on preventing this during continual retraining in language models, where models need to adapt across multiple domains. Another issue is loss of plasticity, where models lose the ability to learn new information over time. A paper I'm studying introduced utility-based perturbed gradient descent to tackle both issues. This method helps models retain old knowledge while remaining flexible to learn new tasks, making it a significant advance in continual learning. This is an index of my presentations. In neural networks, catastrophic forgetting occurs when a model learns new tasks but forgets old ones. This is a major challenge in continuing learning, where models must adapt to new information without losing past knowledge. I capture the image for you understand more easily. One common approach to address this is through the technique that train the model on new tasks while periodically revisiting old tasks. This helps the model retain previous knowledge and continue learning effectively. This balance between learning new information and retain old knowledge is key to overcoming catastrophic forgetting in AI. Another way is the parameter isolation method. It expands to accommodate new information without significantly affecting the previous knowledge. And then you can see another ways in this slide, and then that explain the way of using the regularization method, and then method of the weight update kinds of the using the connection, and then do not affect many weights in the parameter. This page show the challenge as the plasticity. Neuroplasticity is the brain's ability to change its neural circuit through the growth and reorganization. Broadly, it refers to the property where the expression of a certain genotype changes in a specific direction according to the environmental factors. This plasticity also applies to AI, which is designed to mimic the human brain. Recent studies have shown that the optimizer like SGD, stochastic gradient descent, and ADAM cause a loss of plasticity. This is another challenge in continual learning. Solutions to address this issue include methods like injecting the noise, expanding or modifying the system with generate and test approaches, and using the adapters or regularizations. This slide explains both issues and how to address the both issue. In addressing the stability plasticity dilemma, first introduced by Kapner and Rosbach in 1987. The challenge lies in balancing the need to retain previous knowledge while learning new tasks. Initially, effort in continual learning focused on preventing forgetting. However, recent methods are tackling both plasticity and forgetting. The Chandri et al. Proposed the artwork, and then that method, a regularization-based approach. It adjusts to change in weight improvements. And another person, Zhang et al., suggests the technique like the structure-wise distillation loss and pre-training, while Garbus et al. Explore the connection rewiring in sparse networks. And then another person, Kim et al., recently recommended using the sparse network for U&O tests. However, despite these innovations, many methods still face challenges in streaming learning, where task boundaries or reply buffers aren't always clear. This page is the last part of the challenges and related works. Maybe you know the neural network pruning. Neural network pruning is the important measure. It involves removing certain weight to make the network more efficient. The decision of which weight to remove is based on the specific metric. Common approach include using the weight magnitude, which was explored, and using the information from the gradients, like first order and second order information. Last research, Moser and Smoklowski used the first order information, while Luchon et al. Used the second order information. Similar to pruning, methods that prevent catastrophic forgetting also rely on weight improvements, often using the technique like the Fisher information to apply penalties where needed. And then right side images explain the way of the neural network pruning more easily. If we have the model on the right side, about some kinds of the synapse or some kinds of the neurons doesn't need anymore, and then we can prune the model, and then when we use these kinds of the method, our model more light and then have the good performance some way. So the reason is why we use the neural network pruning. This section is the method. Before covering the main method, I have summarized the notation to help with understanding. If there are any difficult elements on the following pages, you can refer to this page. Before start, I define what is the weight utility. Weight utility defined as the change in the loss when setting the weight to 0, and then essentially removing its connection. In the notation is the following this, and then you have to know that these kinds of the loss function, and then W, and then this way the term. This is the where the W Lij utility is set to 0. So if it is set to 0, it's the same to the W and not Lij. J. And then each layer activation function is sigma, and weight matrix is the W. And for the propagation process contribution to computing the output. Yeah. And then this is the activation input to the layer L before the applying the activation function. Before I told you the W and Lij, this term is the WLij set to 0. So you can see that this term is the counterfactor loss, where kinds of the W are not Lij is the same as the W expect the weight W is set to 0. This page explains what is the method, utility-based pursuit gradient descent. You can see the this utility, and this method approximates the utility of the weight by using a second-order Taylor approximation, and calculating the exact utility is complex. So instead of directly removing a weight, and it calculates everything. They estimate how the loss function changes near the current weight, and they use a mathematical shortcut changing how much the loss would change if the weight were set to 0 without actually setting to 0. And overall, the method helps to estimate whether keeping or removing the weight is more beneficial without the need for extra forward pass. Yeah. So over this equation expressing how much a specific weight contribute to the loss function, and then helping us to estimate the utility keeping the or removing the weight. And then this page explain the utility-based part of gradient descent, and then the utility information is to use as the gate for the utility gating, and then utility gate is the weights with the high utility are not updated much by gradient descent, while the unimprovement weights are updated. And then this is the noise. Gaussian noise is applied to the unimprovement weight to help to maintain flexibility. It has to remain the plasticity. And then also you can see the algorithm. And then before start the train, we initialize the all parameters. And then when we start the train, we using the x and y in the data. And then we iterated on these kinds of the steps. And then maximum utility of the weight is the minus infinity, and FL and SL is the compressed list of the numbers, and M1 is the second order approximate, and then utility displayed before I told you, and then also you have on the L can show the means, and then if the maximum utility of the weight is the max, then the utility hat L, this situation, the maximum utility of the weight is the max of the utility hat L. And then layer, or the layer is the took the noise and then projection, yeah. And F1 is the contains the first derivative, and as if the contains the second derivative approximate. These pages show how to evaluate the forgetting and plasticity using the metric. We have the plasticity metric, and then this is the forgetting metric, and then a forgetting metric use the difference in accuracy between two consecutive evaluation windows. So when we have the windows, and then every windows difference, it can have the how to evaluate the accuracy. And then when drop the a second time, it can this situation of the difference can have the evaluate the forgetting in the model. And what is the learned previous tests? Next part is the experiments. These pages show the quality of the approximate utilities. Before the analysis, they use the MNIST, EMNIST, and Cyper10 and IPSINet to evaluate this utility, and then they also use the Spearman's coefficient. You can see this graph, and the red line is the second order utilities, and then it is the correlates with the true utility throughout the learning, and then making it the more accurate approximation. And then first order utility start well, but lose the correlations as learning clutch. So this is the second second correlation in this graph. And then random and weight magnitude utility shows the weak or decreasing the correlation. And then also blue is the loss of the scared gradient utility also, so the below the first order utility, so it is not correlate is the utility. This page also show the experiment whether UPGD against the loss of plasticity. And then right side graph shows the when they take the experiments. First graph shows the accuracy, and X is the task number. When task number are growing, some kinds of the accuracy is the hold in the good side, and then another can losing the accuracy. That side can show we can see the UPGD W, and then both side the non-protection UPGD W, and SEWC also remain the accuracy. But almost other side of the method are the using the accuracy when gathering the task numbers. In that situation, they also even using the graph. Y is the average online plasticity and average online accuracy. When they has the plasticity, also use the accuracy. You can see something. The non-protection UPGY and almost method are going the good accuracy, but does these methods are doesn't good plasticity, but UPGD W has the good accuracy and also plasticity. And then last, shrink and perturb also has the good accuracy, but this method doesn't have the plasticity much. So we can see the UPGDW and SMP preserve the plasticity effectively, but while the method SR work show the poor result in this context. This page is the explain the whether UPGD against the catastrophic forgetting or not. These graphs are the figure number 6, and then when we see this the figure number 6, the UPGD W is the remain the good accuracy when task number are growing. And then this situation also occurs in the B and C. So figure number 6 that the method addressing the improve the online accuracy very well, while methods that don't exploit to handle forgetting, example the Adam W. You can see the Adam W is the red point. Red. It there under around 40% accuracy. So it means when we use the Adam W, it can be it doesn't handle the forgetting as much as UPGD and or other methods. Yeah, and then next page we have the figure number 7 and figure number A, 7A and B, and then that shows the graph, and this show the loss of the plasticity, and then also has the forgetting metric, and then go to the next page. Yeah, this graph, heat map graph shows the forgetting when they test the Cipher and ImageNet, and then with the other methods, and then that situation, the blue point is the good performance, but the more red point is the not good performance in this heat map graph, and also loss of plasticity is the same situation, and then also this graph shows the similar situation. So when we see this of the graph, the UPGD usually control the catastrophic forgetting and then can remain the plasticity as much as well, but uh, almost half of the graph methods are um, struggle the forgetting or the lose the plasticity. Last page is the conclusion. Um, this page shows the conclusion and limitation of this paper and future directions of my research work. While UPGD offers the promising approach for the preventing the catastrophic, it has limitations. One key limitation is that uh, it assumes the utility of the weight is measured independently of the changes in other ways. This doesn't fully capture the complex interactions with the model. Future work could explore the utility measure that accounts for these interactions, potentially improving the method effectively. And retaining important weight is the central to the continual learning, and I plan to incorporate this into my own research. And another challenge with the UPGD is tuning the hyperparameter, while the minimal is still difficult in a life learning context. One potential solution is to apply the generate and test approach, allowing the continuous adaptation of the hyperparameter as the model learns over time. This could enhance the flexibility and performance of models in dynamic environment. Yeah, and then thank you for your attention.